In Chapter 8, we start talking about complex numbers and polars. We're going to take Chapter 8 out of order. I've written the order over here. We'll do 8.1 and 8.2 just like you would expect, but then we're going to jump to 8.5, do 8.3, and save 8.4 for last. Just so you kind of know if I have things out of order, they were intentionally out of order. 8.1 is really just a review of complex numbers. If you have recently done college algebra, you may be fine with working with complex numbers, and this may just be a super quick review. If you struggle with it, then make sure you spend more time on it, maybe do some Khan Academy work and some practice there. By definition, our imaginary number I is the square root of -1, which means that I squared, if I squared both sides of this equation, I squared is equal to -1. We will never leave an I square. We always rewrite it as -1. Okay, so if A and B are real numbers, then any number in the form A plus BI is a complex number. In the complex number A plus BI, A is the real part, and B is that imaginary part because it's the coefficient of I. So if A is 0 and B is not, that complex number is said to be a pure imaginary number. A pure imaginary number, or a number like, or a number such as 7 plus 2i with A not 0 and B not 0, is a non-real complex number. A complex number written in the form A plus BI or A plus IB is in standard form. Now, in general, we keep to the form A plus BI. The exception you're going to see is when you have an irrational value for B. Look in that pure imaginary number box, 3i, negative 2/3 I, and then we have I square root 5. Anytime we have a square root, you're going to see that we put the I in front. Mostly, I believe, just to make sure it doesn't end up accidentally underneath that radical. This is our number system. It shows that real numbers and those complex numbers, non-real numbers, do not intermix. It's either real or it's non-real. Under our non-real complex numbers, we have our complex with the real part and the imaginary part, and then the pure imaginary numbers where A, the real part, is 0. Under our real numbers, we have numbers that are either rational or irrational. Notice that if it's imaginary, if it's complex, then I don't talk about it as being rational or irrational. It's just complex. And I'll just tell you, I usually say imaginary. But if it's a real number, I have to identify whether it's rational or not rational, rational or irrational. My irrational numbers are going to be those irrational constants like pi or e, as well as our radicals that don't simplify down to integers. Rational numbers can always be written as a fraction, so that I have something, even if it's 1, in the denominator. All rational numbers, if I get more specific, I've got integers, which are my positive and negative whole numbers and 0. My whole numbers are my positive integers and 0, so not the negatives. And then my natural numbers are just my counting numbers. This is where, when we learn about numbers, this is where we start with natural numbers, then we add a concept of 0, and we can talk about whole numbers, and then we learn how to deal with negative numbers, and we can deal with integers, and then we move into fractions, and we have rational numbers, add in irrational, and our real number set we typically understand before we get into that concept of complex numbers. Okay. On the next page, we're going to start working with our complex numbers, our imaginary numbers, by simplifying. Notice that if I have square root of -a, that's the same thing as I square root a, and then I want to simplify a as much as possible. So I could think of the square root of negative 81 as the square root of negative 1 times 81. The square root of negative 1 is I, and the square root of 81 is 9. So this simplifies to give me 9i. D is also has a perfect square underneath my radical, so it would be 4i. B is not a perfect square, but and I can't simplify 55. 55 is just 5 times 11, but I can pull that negative out. Notice that I will never leave that negative underneath my radical. 70 is just 7 times 10. 10 is 2 times 5. I don't have any other factors, so no perfect square factors there, so that just simplifies to I square root 70. But when I get over here to 98 and 48, they both are not perfect squares, but they have perfect square factors. So I want to identify that perfect square factor. 98 is even, so let's think about maybe dividing out the 2. So that negative would be negative 1 times 2, and if I divide 2 out of 98, I'm left with 49. Well, 49 is a perfect square. The square root of 49 is 7. The square root of negative 1 is I, so 7i square root 2. I can't pull that square root 2 out. It just has to stay there. Same process here. 48, negative 48. If I look at that, I'm going to think, okay, negative 1. I know 48 is divisible by 4. It would be 4 times 12. And you know what? 12 is also divisible by 4. 48 is actually 16 times 3. So I'm looking for that greatest perfect square. Square root of 16 is 4. What if, though, I didn't see that square root of 16? What if I just said negative 1 times 4 and then times 12, and I saw that 12 is 4 times 3. So 3 times 4 is 12, times 4 is 48. Well, square root of 4 is 2, square root of 4 is 2, and 2 times 2 is 4. Then that gives me my I, so I have 4i square root 3. Now let's solve some equations with these imaginary numbers. We've got x squared equals negative 144. Well, how do we solve this square? We take the square root of both sides. When we take the square root, we consider plus or minus because we don't know if that x started out as positive or negative. So when I take the square root of both sides, I always consider plus or minus. The square root of x squared is just x plus or minus the square root of negative 144. So that is a negative, or excuse me, not a negative. That is 12i. 12i. Square root of negative 144 is 12i. So we've got plus or minus 12i, which means I have two solutions. I can either leave that stacked plus or minus, or I can say negative 12i, positive 12i. I don't have to say positive 12i. On B, I would have to move that 75 over so that I have x squared equals negative 75. So I have, take the square root of both sides, consider plus or minus. So x is plus or minus, and then 75 is not a perfect square, but it has a perfect square factor. 75 is 25 times 3. So I have 5i square root 3. You guys go ahead and work out C and D. I'm just going to give you the solution set because hopefully this is pretty much a review. That's your solution set for C and D. And let's look at the next page. On example 3, we're going to solve a quadratic equation that has a complex solution. Well, if it has a complex solution, that means it's not factorable. But let's go ahead and put it in that standard form anyway to check. This would be 2x squared minus 2x plus 5 equals 0. 5 is prime, it's just 5 and 1. So my signs have to be the same, which means I'm either going to have 10 and 1 or I'm going to have 2 and 5, and neither way do I get a negative 2 in the middle. So I'm going to have to use my quadratic formula. Quadratic formula says x equals plus or minus square root of negative b plus or minus square root b squared minus 4ac all over 2a. It's early this morning, and I obviously was not awake enough to do math. Negative b plus or minus square root of b squared minus 4ac all over 2a is my quadratic formula. Since this isn't factorable, I'm going to use my quadratic formula to solve. I've got that plus or minus and that square root in here. If this value, the discriminant is what we call this value under the radical. If it's negative, then I have two imaginary solutions. So negative b would be a plus 2, positive 2, because that's the opposite of b, plus or minus square root of b squared minus 4 times a times c all over 2a. And I start simplifying. Well, this simplifies to give me 2 plus or minus square root of 4 minus 40 all over 4. And I'm going to come down and say, well, that's going to be 2 plus or minus square root of negative 36 over 4, which is 2 over 4 plus or minus 6i over 4. 2 over 4, 2/4 is a half, plus or minus 3/2 I. And that's my solution set. Those are my two solutions. All right, let's do the next one. Again, we're going to get it in standard form so that I know what the signs are, algebraic signs of each of my terms. And when I plug it into the quadratic formula, I know what values I'm using. So I have 6 plus or minus square root of 6 squared minus 4 times 9 times 5. Well, that would be a negative 6 quantity squared, but when I square it, it becomes positive. All over 2 times 9. So that would be 6 plus or minus the square root of 36 minus 4 times 5 is 20 times 9 is 180. Yep. And then 18 in my denominator. That simplifies to give me 6 plus or minus the square root of a negative 144 over 18. And when I simplify that further, square root of negative 144 is 12i. So my solution set, because I always simplify as much as I can, my solution set ends up being 1/3 plus or minus 2/3 I. Notice I don't keep I in that numerator. Typically I think of that 2/3 as a coefficient because my form is a plus bi. A is 1/3, b is 2/3. All right, when I'm working with negative radicands, remember radicand is the value underneath the radical. When you're working with a negative radicand, use the definition of square root negative a is I times square root of a before doing any other work. What this is telling you is that you need to pull out the I first. Take care of that before you do anything else. So I'm going to pull that negative out from underneath my radical every time first. This one should be I square root 21 times I square root 21. Well, I times I is I square, and square root 21 times itself is square root 21 squared. I squared is negative 1, and this is just 21, so I get a negative 21 as my solution. That's correct. Incorrect would be, for example, if I said, let's start with something different. Let's start with a same situation but different value. If I took square root negative 7 times square root negative 7 and multiplied those radicands together first, I would get positive 49, and I would get a positive 7. That's not correct. Over here, I would have gotten 21 squared is, oh goodness, 21 squared is 441. So I would have gotten a positive 441, and the square root of that would be a positive 21, which would be incorrect. So that is not correct. Make sure you always pull out the negative out from underneath the radical before you perform any other operations. You'll end up in a bad place, a wrong solution. On this next one, that means that would be I square root 5 times I square root 30. Well, I times I is -1, so a negative square root of 5 times 30 is 150, and then I need to see about simplifying that. Well, 5 times 5 is 25, and there are 6 25s in 150. Think quarters in $1.50, there's 6 of them. So that would simplify to be, let's do as a negative, a -5 and then square root 6. Because 25 times 6 is 150, and square root of 25 is 5. All right, on C, I need to make sure I pull out that I first. So that is I square root 42 over I square root 3. Well, I over I is just 1. That simplifies. And I can write, if I have the same index out here, I can write this fraction underneath a single radical, underneath a single radical. 42 divided by 3 is 14. So all I have when I simplify is square root 14. And then finally, let's do this one. I only have a negative value in the numerator, so I pull out that I there. And then I have square root 63 over square root 21. I can put that underneath a single radical, 63 divided by 21. Well, 63 divided by 21 is just 3. So that is I square root 3. Okay, let's look at example 5. It says to write this in standard form. To write it in standard form, I'm going to be pulling out common factors and simplifying as much as I can. I think the easiest way to do this, I'm going to simplify underneath my radicand, and then I'm going to break it into 2 terms, a and then plus or minus bi. So square root -75, we've already done square root -75. We know that that is, only we don't have plus or minus, we just have minus here. That is 5i square root 3. And then I cancel out common terms here, and I have 3 minus I square root 3. And I cancel out those common factors. On the next one, I need to simplify square root of -128. So you're looking for a common factor. If I divide 128 by 2, I get 64, and 64 is a perfect square. The square root of 64 is 8. So this becomes -8 plus 8i square root 2 all over 4. And if I need to think about it split apart, I can do that. And what I end up with is a -2 plus 2i square root 2. And notice when I have that radical, I keep the I in front of it so that I don't accidentally confuse and get that I underneath the radical. Adding and subtracting complex numbers, you just add and subtract the like terms. Make sure if you're subtracting that negative distributes to both terms inside the parentheses. You're going to add or subtract the real parts, and then add or subtract the imaginary parts. Whoops, I got to talking and wrote the wrong thing. I add and subtract the real parts, and then I add or subtract the imaginary parts. All right, so here I'm adding. I have 5 minus 4i added to a -5 plus 8i. Well, 5 and -5 are opposites. They add to 0. -4i and positive 8i give me a positive 4i. Here I'm subtracting. So what I'm actually trying to combine together is -10 plus 7i minus 5 plus 3i, because I distribute that negative inside my parentheses. And then I just combine the like terms. So I have -15 as my real part and plus 10i as my imaginary part. On C, notice that I am subtracting that second imaginary number, so I need to think about changing the signs there. So that what I actually have is 8 minus 8i plus 2 plus 5i minus 10 plus 3i. I'm going to add all my real parts. 8 and 2 is 10, minus 10 is 0. And then the imaginary parts, I've got negative 8i, positive 5i, and positive 3i. Well, those are opposites as well, so everything adds to 0. And let's look at the next page at example 7. On example 7, we talk about multiplying complex numbers, excuse me. When I multiply these complex numbers, I'm just foiling them together. So first product would be 10. Outside would be a negative 35i. Inside would give me a positive 6i. My last product is a negative 21i square. Now take note, anytime I have an I square, that I square is a negative 1. So this is actually a positive 21. So I'm going to take that and I'm going to add 21 to 10 because that's a positive 21. 21 and 10 is 31. And then I have a negative 35 and a positive 6i gives me a negative 29i. Never leave I square in your solution. You're always going to change it to a negative 1. These two terms, again, practice your FOIL. 6 plus 8i minus 9i minus 12i squared. That becomes a positive 12. And I'm left with 18 minus i. Squaring a binomial. Our next two examples are squaring a binomial. When you square a binomial, remember that the outside and the inside products always add to 0. Oh, no. I'm so sorry. I'm already looking down here and talking about E, or about C. On C and F, we are doing conjugate pairs. And with conjugate pairs, our outside and inside terms always add to 0. I was ahead of myself. When I square my binomial, I can either write it out so that I FOIL 4 minus 5i times 4 minus 5i, or I can remember my shortcut. My shortcut is to square that first term, multiply the two together times 2 to account for the outside and inside products. So that would be a negative 20i times 2 is a negative 40i. And then square this last term. Negative times a negative is a positive 25i squared. Well, I squared is a negative 1, so that's a negative 25, and a positive 16 gives me a negative 9 minus 40i. Over here, I'm squaring a binomial again. 16 plus 12i times 2 is 24i plus 9i squared, and that changes sign. So 16 minus 9 is 7 plus 24i. And then we move down here to when I'm doing the conjugate pairs. This is where the outside and inside products add to 0. So 9 times 9 is 81, and then minus 64i squared, which that changes sign and becomes plus 64, so that I have 145. And here I've got 36 minus 25i squared, which changes sign, so that I have 61. Two complex numbers that differ only in the sign of their imaginary parts are called complex conjugates. They work just like our real number conjugates. The product of a complex number and its conjugate is always a real number. So that gives us our property of complex conjugates. To find the quotient, if I have division with two complex numbers, to find the quotient of two complex numbers in standard form, we multiply both the numerator and the denominator by the complex conjugate of the denominator. Now, when I think about this, I remember it as like when we rationalize our denominator, it's kind of like that. When you rationalize your denominator to get a radical out of the denominator, if there are two terms, you multiply by the conjugate. Well, even if there's one term, you multiply by the conjugate. That's what we're doing, is we're multiplying by the conjugate of the denominator in order to perform this division. So we're asked to find a quotient because we have that fraction bar. So we're going to multiply by a well-chosen 1, and my well-chosen 1 is going to be the conjugate of my denominator. Well, in the denominator, I'm going to get a real number because when I multiply two complex conjugates together, I always get a real number. The numerator are not conjugates, so I'm not going to get just a real number in the numerator. I can't expect that. So let's look at the denominator first. 3 times 3 is 9 minus I squared, which is going to become 9 plus 1, or 10, in my denominator. So I'm going to go ahead and copy that down. Now let's go back and look at our numerator. 5 times 3 is 15, minus 5i minus 15i plus 5i squared. So I have, this becomes a negative 5 plus 15 is 10, and then a minus 20i, which is the same thing as 10 over 10 minus 20i over 10, or 1 minus 2i. Let's look at B. The conjugate of negative I is just positive I. So I'm just multiplying this times I over I, which gives me 15i over negative I squared. Negative I squared is just positive 1. So my solution is just 15i. On C, my conjugate is a negative I. So I have a negative 3i in my numerator and a negative I squared in my denominator. Again, negative I squared is just positive 1. So my result is a negative 3i. Let's talk about those powers of I. The powers of I cycle through. And this is kind of fun once you notice what the pattern is. We know that I to the first is just I, and I squared is negative 1. Well, if I have I cubed is the same thing as I squared times I, where I squared is negative 1 and I is just I. So that would be a negative I. And then I to the fourth is just I squared times I squared. Well, I squared is negative 1, so that's a positive 1. And I to the fifth is just I times I fourth, correct? So let's change colors here. I to the fifth is just I times I to the fourth, which is just I times 1, because I to the fourth is 1, so that's just I. I to the sixth is just I to the fourth times I squared. Why would I always go to I to the fourth? Well, I to the fourth is just 1, and multiplying times 1 is easy. So I to the fourth is 1, I squared is negative 1, and 1 times negative 1 is negative 1. I to the seventh is I fourth times I cubed. I to the fourth is 1, and if I look up here at my pattern, I cubed is negative I, so that is negative I. And then I to the eighth is just I to the fourth times itself. I to the fourth times I to the fourth, or 1 times 1, which is 1. And I want you to look and see what we're doing here. We've got I, negative I, 1. Excuse me, there we go. I lost my negative 1. I, negative 1, negative I, 1. And then we do it again. I, negative 1, negative I, 1. And that's the pattern that is just going to keep repeating through. Those are the only 4 possible values of I to any power. The powers of I are going to cycle through those same 4 outcomes. I, negative 1, negative I, 1. And since I to the fourth is 1, it has the same multiplicative power property as 1. Any power of I with an exponent that is multiple of 4 also has a value of 1. So if I can rewrite, for example, let's see, for example, I to the 20th is just the same thing as I to the fourth 5 times, right? Because 4 times 5 is 20. Well, I to the fourth is 1, and 1 to any power is just 1. So if I can reduce my exponent to just a certain number of I to the fourths, it's just a whole bunch of 1s times itself. And that's how I simplify my powers of I. I look to see how many times I can pull out I to the fourth and see what's left over after that to figure out what my solution will be out of that pattern. Okay, we're going to do our positive exponents first, A and C, and then we'll come back and do these negative exponents. So for A, I have I to the 33rd. Well, how many times can I pull I to the 4th out of I to the 33rd? That would be I to the 4th times what? 5 times 4 is 20, we said. 6 times 4 is 24. 7 times 4 is 28. 8 times 4 is 32. That's as close as we can get. 8 times 4 is I to the 32nd, which means I have one more I left over to get my 33 I's. I've got 32, 33 I's. Well, I to the 4th is just 1, so that's 1 to the 8th times I. 1 to the 8th is just 1, so my result is I. I to the 15th. How many times do I have I to the 4th in I to the 15th? Well, I to the 4th, 4 times 4 is 16, so I can go 3 times. 4 times 3 is 12, which leaves me with I cubed left over. This piece is just 1 because I to the 4th is 1 and 1 cubed is just 1. So I've got I to the 3rd left. If you don't remember what I to the 3rd is, you at least know that's I squared times I, and I squared is -1. So I cubed is -I. Notice that where I have an odd exponent, I have either I or -I. If I have an even exponent, I'm going to get 1 or a -1. All right, let's think about how to deal with negative powers of I. The easiest way to deal with a negative exponent is to multiply by I to the 4th, by 1, multiply by 1, which is going to look like I to the 4th, enough of them to get a positive exponent. Okay, because I can always multiply by 1. It doesn't change the value. Let's think about that and what that looks like. If I had, let's say 1/2. If I multiply that by 2 over 2, 2 over 2 is just 1. 1/2 is equal to 2/4. Those are equivalent fractions. So I can always multiply by 1. It doesn't change the value of what I have. That's what we're going to do. We're going to multiply by 1 in the form of I to the 4th until we have a positive exponent. Well, my first exponent is just -3. I can just multiply that by I to the 4th, just that, and I have a positive exponent. -3 plus 4 is I to the 1st, which is just I. Okay, let's do the next one. I to the -14th. Well, I need to pull in more I to the 4ths here. 4 times 4 is 16, right? So I to the 16th. I to the 16th is I to the 4th 4 times. And if I add my exponents here, -14 and a positive 16 is I squared. And we know that I squared is -1. Notice I had a negative exponent. My answer is a form of I. I have a positive exponent. My answer is a form of 1. If I have negative exponents, my answers will always be I or -I. If I have a positive exponent, I am saying this all backwards today. I hope you guys are sitting there correcting me at home in your heads or even out loud. I'm saying the wrong terms. I'm thinking what I mean, but I'm saying it wrong. If I have an even exponent, I get 1 or -1. If I have an odd exponent, I get I or -I. For example, 33, 15, and -3 are odd numbers. The result is always going to be I or -I if my exponent is odd. However, if my exponent is even, like 20 or -14, my result is going to be 1 or -1. And I absolutely apologize for that confusion.